In our previous classes, we learned about different properties of determinant. Today we will start with the process of increasing and decreasing the order of a determinant. And this I will discuss with an example. Let A is equal to the determinant. I will start with a second order determinant. Say 5, 8, 7 minus 2. This is of second order. Now I will transform it to a third order determinant. Now see how I am doing this. I am writing 1, 0, 0, 0, 0. After that 5, 8, 7 minus 2. Now see, this is of third order. Now these two determinants are have same value. Why? On expanding this determinant with respect to first row or first column, you will get this determinant. Now we can furthermore write it in this way: 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 5, 8, 7 minus 2. So this is of fourth order. Because on expanding this determinant with respect to first row or first column, you can get this determinant. And again, expanding this determinant with respect to first row or first column, you will get this. Now see, this is not mandatory to write all these four elements 0. You can write these elements at 8 or 10, keeping these to 0. Then on expanding this determinant with respect to first column will give you the first given determinant. Likewise, you can write this determinant as 6, 10, 8, keeping all these 0, and on expanding this determinant with respect to first row, you will get this determinant. This determinant, that is 8 and 10, and again expanding this determinant, we will have this determinant. So this is the process of increasing the order of a determinant. Now, next method, how to decrease the order of a determinant. This I will discuss with an example. Let A is equal to 5, 7, 10, 3, 6, 9, 8, 4 and say 11. To decrease that order of a determinant, I will convert any row or column in the form in which the row contains or column contains single non-zero element. That is, the row will looks like, say second row, it may looks like 0, 1, 0. Or 0, 5, 0 or 0, non-zero. Not necessary it is 1. So I converted, if I convert first row, or of the form 5, 0, 0, dash, 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 and this like this. So first column contains only one non-zero and all other 0 element. Second row contains only one non-zero element and all other elements are 0. Because on doing that, if I expand the determinant with respect to that row or that column, we will have a reduced order determinant. To convert a determinant of this form, first we will observe the elements. Now from the elements of this determinant, note that 6 is 2 times 3, 9 is 3 times 3. So if I subtract 2 times first column from the second column, this becomes 0. Don't bother about other two elements. If I subtract 3 times of first column from the third column, this becomes 0. Again, don't bother about the other elements. So this is a property. I will apply this. What I did, C2 dash new column that is represented by C2 dash is C2 minus 2C1. C3 dash is C3 minus 3C1. Now see, this row has single non-zero element. So I will expand this determinant with respect to this row. So it will be 3 into its cofactor. It is 2, 1 element into, to get it cofactor or minor, I have to eliminate this row and this column. So minus 3, minus 5, minus 12, minus 13 only remains. Now see, this is of second order. So order of the determinant reduced. Now if there is no such row where all the other elements are some multiple of any element, then what will happen? So I am forgetting about this determinant, this row. I am not using this row property, this property. In that case, you have to convert any element, any of these 9 elements to 1. Any of these 9 elements. How could you do this? You can do this in plenty of ways. First of all, if you want to convert these to 1, take 5, divide this row by 5. This will become 1. This is 7 by 5. This is 10 by 5. That is 2. If you want to convert these to 1, take 3 common from this row or this column, common of that element. Divide that row by that non-zero element. Or you can subtract this row from this row and that will convert this to 1. Because 10 minus 9 is 1. You can subtract this row from this row. This will convert this 11 to 1. So there are plenty of options. You can subtract 2 times of this row from this. This will become minus 1. And minus 1 will also serve our purpose. So you can convert any element to plus 1 or minus 1. Now I will convert these to 1 by subtracting this row. So from this we are subtracting second row from first. So 5 minus 3 is 2, 7 minus 6 is 1, 10 minus 9 is 1, 3, 6, 9, 8, 4 and 11. After converting the element 1, what we will do? I will make these 2 to 0 or these 2 to 0. Convert these two. How? If I subtract this column from this column, it will become 0. If we subtract 2 times of this column from the first column, this will become 0. If I subtract 9 times of this row from this row, second row, it will become 0. If I subtract 11 times of row 1 from the row 3, then it will become 0. I have to convert these two 0 or these two 0, not all. In this case, I have to multiply by 9 and 11, and in this case, I have to multiply by 1 and 2. So I will choose these two. Now, a row with single non-zero element is achieved. Now we have to expand this determinant with respect to this row. So it is 1 into, it is my 1, 3 element, 1 plus 3. You have to redo eliminate this row and this column. So minus 15, minus 3, minus 14, minus 7. Now see, this is of second order. And our goal is achieved. Now this is our first example. Now the time arises to apply the properties of determinant to solve different problems. Now this is our first example for today. Show that the roots of the equation, this is a equation, because on expanding this determinant you will have a polynomial of x. So it is a polynomial equation expressed in determinant form, are independent of m and n. Answer: we have x m n 1 a x n 1 a b x 1 a b c 1 is equal to 0. This is our equation. In this equation, note that all the elements of this column are 1. If we get a row or column whose all elements are 1, then it will be treated as prize opportunity, because you can make all other except 1, all other elements to 0 by subtracting first row from others, or second row from the others, or third row from the others, and then expanding this degree of this determinant will be reduced. So I'll apply the process, or keeping first row intact, x m n 1, I subtracted first row from the second, so it becomes minus x minus m, n minus n 0, it is also 0. So what I have done, R2 dash is R2 minus R1. Similarly, first row is subtracted from third. That gives you a minus x, b minus m, x minus n and 0. So R3 dash is R3 minus R1. And likewise, a minus x, b minus m, c minus n 0. What I have done? R4 dash is R4 minus R1. This is explanation, equal to 0. Now see, all other elements except 1 become 0. So on expanding with respect to third column, what we get? Now see, plus minus plus minus. So it is minus 1. It is 1, but it minus 1 because minus 1 to the power 1 plus 4 is multiplied. So it becomes minus 1 into equals 0. In this determinant, see, all elements of first column are a minus x. So what we have done? Expanding with respect to first column, or so minus 1, it is equation equal to 0. So no matter, I can reduce this minus 1. So a minus x into 1, 1, 1. What I have done? A minus x is taken common from C1. C1 means first column. Now see, again I have a column whose all elements are 1. The same process I will apply. Again, a minus x, since all elements are 0, I will expand it with respect to first column. I will expand this determinant with respect to first column. On expanding, it becomes 1 into equals 0. Expanding with respect to C1. Clear? Or now again take C, b minus x is common. So a minus x into b minus x into 1, 1, x minus n, c minus n equals 0. So you can write the explanation. Now after that, again we get a column whose all elements are 1. But in this case, since it is second order determinant, we won't apply the previous method. We just expand it. Or a minus x into b minus x on expanding, c minus n minus x plus n equals 0. Now see, x is a, b or c. So all the values are independent of m and n. See, all the values are, solutions are independent of m and n. Now see, our next example is prove that n factorial, n plus 1 factorial, n plus 2 factorial, and this determinant, value of this determinant is n factorial into n plus 1 factorial into n plus 2 factorial into 2. Answer. Let D is equal to this is equal to D. Now see, n plus 1 factorial is n plus 1 into n factorial. N plus 2 factorial is n plus 2 into n plus 1 into n factorial. So we can write this as n factorial, n plus 1 into n factorial, n plus 2 into n plus 1 into n factorial. Similarly, likewise, we can write the third column, a third row. Now see, from the first row, n factorial, we can take n factorial common. So what we get? From the second row, we take n plus 1 as common. So it becomes 1. And from the third, we take n plus 2 factorial common. That gives you. So one part of the result is already achieved. So we have to show that value of this determinant is 2. Then what we do? N factorial, n plus 1 factorial into n plus 2 factorial. Now see, we get a column whose all elements are 1. So I already told this is a price situation. So in this case, I will subtract first row from the second. So keeping first row intact. First row from second, this becomes 0. So this minus this gives you 1. This minus this gives you n plus 2 will come common, and n plus 3 minus n plus 1, that gives you 2. So what I have done? Similarly, I subtract R2 from R3. R2 from R3. So n plus 3 minus n plus 2. That gives you again 1. And when you subtract this from this minus this, n plus 3 comes common. So n plus 3 and remaining are n plus 4 minus n plus 2. That gives you 2. Now see, this column becomes 1, 0, 0. So I can simply expand it with respect to first column. That gives me now I will just expand it because it is of second order, just expand it. Now see, this is nothing but 2. So result follows n factorial into n plus 1 factorial into n plus 2 factorial into 2. Now our third example. If A not is equal to P, B not is equal to Q, and C not is equal to R, and the determinant P, B, C, A, Q, C, A, B, R equal to 0, then find the value of P by P minus A plus Q by Q minus B plus R by R minus C. Solution. Let delta is equal to clear. This is equal to P, B, C. First row remains unaltered. I subtract first row from the second, so it becomes A minus P, Q minus B, 0. I subtract second row from the third, this becomes 0. That is B minus Q, and this is R minus C. What I have done? Now I divide this column by A minus P. So I have to multiply the determinant with A minus P to keep the value same. So it becomes, I divide second column by B minus Q. Second column by B minus Q. And third by C minus R. So it becomes C. Now you can just expand this. Now you can just expand this with respect to first row. What we get? Into P by A minus P. 1, 1, 1 minus 0. Minus B by B minus Q. Into what we get? Minus 1 plus C by C minus R into 1. that is equal to into P by A minus P minus, see it is minus 1 plus B by B minus Q. I subtract minus 1 from here and add 1. Why? To make it Q by B minus Q. Our question is Q by B minus Q. On subtracting minus 1, it becomes Q by minus Q. Similarly, it is C by C minus R. I subtract my 1 from here and plus 1 is there. So it becomes, now see this is equal to 0. Now see this is equal to 0 according to the question, because this delta is 0. And A not is equal to P, B not is equal to Q, C not is equal to 0. So these are non-zero. So this is equal to 0. And that will give the answer. Note that it is P minus A, it is A minus P. So it is minus of P by P minus A. That will gives you this is equal to 2. That will gives you this is equal to 2. This is our answer. Now comes our fourth example today. This is a very big sum, lengthy sum. You have to show value of this determinant is 2 into AB plus BC plus C whole cube. Solution. Let D is equal to copy the determinant. Now see this is equal to 1 by A square B square C square. Why this written? I will multiply the first row by A square. That's why A square is divided here. So it becomes A. I will multiply this second row by B square. That's why B square comes here. Likewise, multiply third row by C square. Assume that AB is X, BC is Y, and CA is Z. Then note that A square B square C square is XYZ. So let this. So the sum becomes 1 by XYZ assuming this, the determinant reduces to this format. Now in this XYZ, I subtract second row from first row. What we get? R1 dash is equal to R1 minus R2. Next I subtract R3 from R2. So R2 dash is R2 minus R3. Since it is of third order, you can apply maximum 2 row operations simultaneously. So now see this is XYZ. Now you notice that this is X plus Y plus Z into X minus Y plus Z. This is x plus y plus z into minus x minus y plus z. This is 0. This is 0. This is x plus y plus z into x plus y minus z. This is x plus y plus z into x minus y minus z. Now it is easily, you can see that x plus y plus z comes common from, you can take common from first row and as well as second row. So that gives you x plus y plus z whole square by xyz. Here remains now see x plus y plus z is nothing but AB plus BC plus C. So you have to show that AB plus BC plus C whole cube. Already whole square is arrived. After that, what we will do? We'll do x plus y plus z whole square by xyz into. So x minus y plus z 0 y square remains unchanged, minus x minus y plus z, x plus y minus z and z square remains unchanged. I added these two row. Now see, on adding these two row we get x eliminated, so 2z minus 2y. I subtracted 2 from this. So 2z minus 2y subtracted from this, so it gives you 2 into y minus z. I added these two, so only this is the sum. When I subtract this from this, what we will get? Minus z cancels, x cancels, only minus 2y remains. When sum of these two is subtracted from this, remains minus 2yz. So C3 dash is equal to C3 minus C1 minus C2. Okay. What we will do next? X plus y plus z whole square by xyz into. Now I will add row 2 with row 1. X minus y plus z. These two are added, z cancels, y cancels and x cancels. It becomes 0. And when these two are added, my plus 2y minus 2z minus 2y. So it is minus 2z. This. What we have done? Next, see, it is a. I can take 2 common from there, minus 2. We can take my, it is plus, sorry, plus 2yz, this will be plus. I can take 2 common there, I won't take 2 common now. Now I am willing to make these two 0. Then I can expand the determinant with respect to third column. What I will do for that? I will multiply this row by y. So y is there and this row by z, yz. Y. Now see, all elements are same, only sign differ. So in this step, I will apply y plus z whole square by yz into xyz into. Now I add third row with first row, then this becomes 0. Third row with first row. Now see, in the first row, this is xy minus y square plus yz. When y square is added, it becomes y into x plus z. When these two are added, it is z square. It is 0. Similarly, I will add third row with second row. Now I can expand the determinant with respect to this column. So that is x plus y plus z whole square by yz into xyz 2yz plus minus plus minus plus, this is plus element. So 2yz into its cofactor. What is its cofactor? Now yz cancels. Now you just expand this. What we will get? X plus y plus z whole square by 2 into xyz into this. So yz into z plus x into x plus y. So it is x square plus xy plus xz plus yz. Multiplication done, minus y square z square. Now see, if you take yz common from these two, 2 into x plus y plus z whole square by xyz. Take yz common from these two. What we will get? X square plus xy plus xz plus yz minus yz. So yz cancels. Yz cancels. So that gives you 2 into x plus y plus z whole square by x, and x comes common from here, x into x plus y plus z. So x cancels. That gives you 2 into x plus y plus z whole cube. That is 2 into x is AB, BC, CA whole cube. Now, fifth and last example of the day. If sin x, sin y, sin z, cos x, cos y, cos z, cos cube x, cos cube y, cos cube z, this determinant is 0, then at least two of x, y, z are equal. That is, either x is equal to y, or y is equal to z, or z is equal to x, or x, y, z all are equal. Or x plus y plus z is n pi plus minus pi by 2. The solution. Copy the determinant is equal to 0. That implies, now I divide first column by cos x, sin cos x. That gives me tan x. Sin x by cos x, 1 cos square x. Second by cos y, so it is tan y, 1 cos square y. Tan z, 1 cos square z. Into, since I divided first row by cos x, I have to multiply it by cos x. and cos y and cos z, that is equal to 0. So cos x, cos y, cos z become. And why I did this? To get this row, all elements are 1. So a prize is in my hand. Or tan x 1 cos square x remains unaltered. I will subtract first column from the second. Second column from third column. Into cos x, cos y, cos z equal to 0. You can't claim cos x is equal to 0 here. Because if cos x is 0, you can divide it by this. Now what happened? A row with only one non-zero element is achieved. So I will expand it with respect to second row. So mine. Now see, this is equal to minus cos x, cos y, cos z. We know that tan A minus tan B. Tan A minus tan B. This is sine of A minus B by cos A cos B. Tan A minus tan B is sine of A minus B by cos A cos B. So it is cos y cos x. It is, and cos square x minus cos square y. Cos square y minus cos square x. What we can write it? We can write it sine of x plus y into sine of x minus y. We can write it sine of x plus y into sine of x minus y. And cos square z minus cos square y, we can write it sine of y plus z into sine of y minus z equals 0. Formula. So sine of y minus x, we can take common. Sine of z minus y, we can take common. And after that, we'll expand this too. And on expanding, and also cos y. Also cos y from first row. So, proceeding this way, we can show that. So, we can take common this. We can take common this from the first row. And after that, we will expand the determinant. After expanding, what we will get? We'll get this expression sine of x minus y, sine of y minus z, and sine of z minus x into cos of x plus y plus z equals 0. So rest you have to do. I have already said y minus sine of x minus y is coming common. Sine, you can take sine of y minus z common from these two. And this is symmetric about x, y, z. If y replace x by y and y by x, the determinant equation remains unaltered. So from the symmetry, this, if x minus y is, sine x minus y is a factor, then sine y minus z, sine z minus x are also factors. And after multiplication, you will have cos of this. And from this, the result follows. So students, today I discuss two methods of increasing and decreasing order of a determinant. After that, we have 5 examples of the problems in which we applied the properties we learned. In our next lesson, video lesson, we will show some more examples. So that's all for today. Thank you.